Hi guys, this is Timothy, and today we're going to go over Math Club's Meeting 25 material. So yeah, most of these questions are taken from Art of Problem Solving's intermediate and probability textbook, and I believe some of these problems might be quite challenging, and other ones will be pretty intuitive. Um, yeah, right now we're only working on the first chapter, so um, the material in this chapter should be pretty simple, and we're probably gonna expand into more difficult chapters later on. So yeah, our first question starts off with a pretty simple permutation question. Um, I'm gonna give everyone a bit of time to take a look at it, and you can pause the video if you want. So yeah, for this question, what we want to do is we do need to realize that it did say that the order of the selected combination does matter, which means that A, B, C, D, if we select this ball in this order, is different from B, A, D, C. So even though they're the same four balls, they're selected in different order, and this concept is called permutation. So permutation is, yeah, as I mentioned before, it's basically selecting, let's say, a certain amount of items from a large group, and without replacement, we want to know the number of ways to choose all these items where the order does matter. In this case, how do we approach this question? So let's just say this is our first ball that's drawn out, and then this will be our second, third, and fourth ball. For our first ball, there's going to be 25 combinations, as there will be 25 balls in the box. And as one ball is taken out, this is for question 8, as one ball is taken out and discarded, we're going to have 24 balls left to choose from in the box. And after that, we're going to have 23 left because we drew two balls out. And then we're going to multiply it by 22 as we took three balls out. And then, yeah, that's going to be a total of 30, 303 cells and 600 combinations. And for B, when the balls are kind of replaced back into the bin after it's removed, um, we're gonna have to kind of think differently. So yeah, for this question, basically what we do is we have 25 choices for the first draw, and then after the first draw, we put the ball back in, which means that during our second draw, there's still 25 combinations. And this same thing occurs for our third and fourth draw, making this 25 to the power of 4 as our final answer, which is around 390 cells and then 625. So these are our yeah, answers for this first question. This question is one of the easiest questions in the textbook, and I hope everyone is able to fully understand the concept. And our second question is going to be a bit more difficult. It talks about a dog breeder separating his 10 puppies into a group of 4 and a group of 6. Um, but he has to keep these two dogs in separate groups. So there's a lot of ways to think about this. And one of the ways I do want to think about this is using two concepts. So the first thing I want to talk about is complementary counting. So so yeah, basically how does this concept work is it's basically choosing the total. Okay, let's think about it this way. So if we want to count the number of items, let's say count the number of items A, we can think about it as having the total items and then subtract it by the ones that are not A. The Yeah. So yeah, we can think about it something like this. And the second concept that I want to talk about is called casework. Basically, this one is um, just breaking up, um, I guess, breaking up possibilities into um, more subcategories. Um, it's it's pretty hard to explain how these work without showing you guys an example. So I guess I will just do this question. So yeah, um, first thing we want to know about complementary counting is we want to find the total amount of well, the total number of groups that we can achieve by separating 10 puppies into a group of 4 and a group of 6, and subtract it by basically the total number of counts um, of these two groups where this bitter and nipper are together in the group. So basically we can say, um, I guess our answer can be written as total ways to separate 10 puppies and then minus total ways into group of 4 and group of 6, of course, um, to separate 10 puppies in group of 4 and group of 6 in which bitter and nipper are together. So yeah, what we do here is we can calculate the total number of ways to separate 10 puppies into a group of 4 and a group of 6. How do we do this? We can simply do 10 choose 4 as we separate 4 of the puppies from the 10 groups, and then the other 6 will automatically be listed as the other group. And yeah, so this is total. Now we can think of the ways to separate 10 puppies into a group of 4 and a group of 6 in which bitter and nipper are together. So how can we do this through casework? What we can do is first calculate the number of ways we can do it so that B and N are in the group of 4. So um, if B and N are in the group of 4, this means that they're going to be with 2 other dogs. And the number of possibilities for the 2 other dogs is going to be 8 choose 2, as um, we choose from the 8 remaining dogs, and we choose 2 of them to put into the smaller group with um, what's the name? Bitter and nipper. So that's going to be the number of possibilities we have when B and N are in the group of 4. And similarly, we want to calculate the possibility that B and N are in the group of 6. So what we do here is we do the same thing. There's 8 remaining dogs, and we need to choose 4 other dogs to put in the larger group to be with Bitter and Nipper. And that's going to be our answer. So what we do is we use 10 choose for the total number of possibilities minus all the ways that Bitter and Nipper are together. And we would get 210 minus 28 plus 70, which is 112 as our final answer. And yeah, so this is going to be our last question. This question is, I would say, slightly more challenging than the previous ones. So yeah, try our best to take a look at it. And yeah, um, one important note that I want to mention before we start doing this question is when approaching these kind of probability problems, we want to be sure to remain consistent. So for example, if we want to count the successful outcomes with regard to order, we shouldn't count the total number of outcomes without regard to order. So yeah, um, in this case, we didn't count the order of the puppies because we don't need to. And in a more complicated question, um, we need to make sure that we either count all the, we need to make sure first of all whether they want us to count um, the different orders or not. If they do, then make sure throughout the whole question, we need to separate all their orders. And if they don't, then we also need to make sure throughout their whole question, the order doesn't matter. And yeah, so one wrong example would be in calculating the total number of cases over here, we kind of used 10 times 9 times 8 times 7 to kind of determine the total number of choices instead of using 10 choose 4. As in this case, the order of the puppy does matter, and that's not what the question wanted. So yeah, let's get back to our question 3. In this question, what we need to think about is, so I believe that we can separate this into kind of two subtasks. First of all, when we notice that it is gonna be like a um, I guess a full house is basically 3 cards taken from one rank, and 2 cards taken from another rank. And yeah, the total possibility is basically 5 random cards taken from the deck. Since we can tell the order of the cards doesn't really matter, um, let's try to solve this question this way. So let's calculate the total possibilities first. This should be easy. It's just going to be 5 choose, my bad. 52 choose 5. 52 cards, we pick 5 random cards out and see their combination. And let's solve for these 2 cases. So 3 cards taken from one rank. What we need to do here is we first need to determine how many ranks are there. So we want to choose one rank out of the 13 ranks in each deck of cards. So that's going to be 13 ranks. And within each rank, there's going to be 4 cards. And within the 4 cards, we only want to choose 3 of them. So we're going to have 13 times 4 choose 3 as the possibility that 3 cards are going to be taken from one rank. And then what we want to do is we want to multiply this by the second possibility, which is what's the possibility of 2 cards being taken from another rank. Since we already took one rank, it's not possible for us to have this rank to be equal to this rank, as there's only 4 cards in each rank, and we want 5 cards here, right? So we're gonna have 12 ranks left, and then within each rank, there's gonna be 4 cards for this new rank. And then what we want is we want 2 cards in that rank. So we're gonna have 13 times 4 choose 3 multiplied by 12 times 4 choose 2. What we're gonna get here is 3,477, and the number of possibilities here is 259. Actually, this is pretty big. Yeah. So 2,596,960. Yeah, so this is going to be our total possibilities, and this is going to be our possibilities of successful cases. And yeah, in the end, we're going to get this. This is our final answer. So yeah, thank you so much for watching this video. And yeah, we'll see you guys next time.